So again, recall our permutation character. So in terms of normal character, you write it like this, but we said permutation character is special, so we denote it by pi of x. So this is just the elements of the set x which are fixed by g. So now we want to prove this result called Burnside lemma. So you take this permutation character and you take a trivial character, take their inner product. This should be equal to number of orbits of g on x. So we can write this x as the disjoint union of orbits x1, x2 all the way to xk, and which would immediately imply that this cx is like this because of the linearity of the g action. So g action would restrict to x1, it would restrict to x2, xk, so all of these wouldn't get mixed up. So this implies immediately this. And since you have this, now you can take the permutation character, which will just add up like this, because there are no n1, n2 sitting here, all of them are just powers of 1. So then just one copy. So you have this. So till now you split it like this, becomes like this, and where each of these is a permutation character. So x1 corresponds to this, xk corresponds to this. So in order to prove the theorem, we just have to prove it for one of them, just for the transitive action. So just for one orbit where the action is transitive. So what we are going to do is you're just going to take one of these, call it x, rather than this x, just take one of these which is x, and then you have this inner product with trivial character. This is again the trivial character. We should get 1, and then you add it over all of them, you will get the number of orbits. So suppose g acts transitively on x, we want to show this as 1. So that is it. So we just use the definition of our inner product here, which is this. You're working over the group G, but this is a real number, so generally we do a conjugation here. So there is no conjugation here because this permutation character is real. It's just a size of the group. So it's not a complex number, it's not going to change. So now you're grouping. So now this pi x of g has this definition, but you're summing it, so you have this another element g. So we are copying this down right here. We're putting an extra factor of this g here because of the sum. Now this you can rewrite it as now sum it over x and have the stabilizer. So this is the stabilizer of x. This is the stabilizer of x, but now we are summing over the set x rather than the group G. Here we were summing over the group G. Now we have come here to summing over the set x. Now recall the orbit stabilizer theorem. We have this size of the stabilizer times size of set x is the size of group G. So we can rewrite this. Instead of stabilizer, you are writing this size of G divided by size of x. So this is replaced by this. That is it. Now you sum it over all x, you get size of x. This summation sign is giving us this. You do the cancellations, and what you get is 1. And that is what we wanted to prove. Now you keep on adding this over all this x1, x2, x3 all the way to xk. That will give you the number of orbits of G on x. Now recall this. If G acts on the sets x1, x2, then you can define the action on x1 times x2 via this gx1, gx2 standard, nothing much to be done. So by definition, this is the number of pairs x1, x2 lies in x1, this x2, which are fixed by G, because the definition of the permutation character is the things which are fixed by G. So all these pairs now which are fixed by G, here would just x, now we are talking about x1, x2 fixed by G, which is the same as number of elements in x1 fixed by G times the number of element in x2 fixed by G. So number of elements in x1 fixed by G is this permutation character. So now you have x1 here fixed by G, number of elements fixed by G in x2 is this. So number of elements in x2 fixed by G, this is right here. So we have this almost trivially. So this permutation character of x1 times x2 is just the product. So now we want to prove this small lemma. This pi x1 x2, the inner product, is equal to number of G orbits on x1 times x2. So now what we will show is that this inner product is actually equal to this pi x1 times x2 comma 1, because then we can use this Burnside lemma. So this 1 is the trivial character. Then we can use this Burnside lemma to show that now actually it will be the number of g orbits, or number of orbits of g on x1 times x2, because instead of x we are writing x1 times x2. So we have to show this is equal to this, but we have just shown that this is equal to the product here. So rather than writing this here x1 times x2, we can write the product, which is right here. So these two are equal from this result right here. So what we need to show is that this inner product is equal to this. So now just do the definition. We have the group, you take the conjugate of the first part, write the second part, just introduce the trivial character, which is does not do anything except multiply by 1. But notice that these permutation characters are always real because they are just the size of the set. So they are real, so you can put a conjugation sign over both of them. So if you put a conjugation sign of both of them, now this is just this inner product right here, because this is the trivial character, which we are often denoting by chi of 1. That is pretty much it. So we are done with this lemma. Let us now record this two-transitive action. So we say that the G acts two-transitively on this set X if the size of X is greater than 2 and G has 2 orbits on this product. So namely this where X and X are the same, and if x1 x2 these are different. Yeah, so pretty standard, either they are the same or they are different. So now this is actually this is useful to understand the symmetric group, since the symmetric group is two transitive other than S1. So forget about the case of S1. So now if we have this two transitivity, we can actually say something more. So say G acts on X, this is greater than 2, then this our permutation character is trivial character, so this is trivial character plus some other character chi, and this chi is irreducible if and only if G is two transitive on X. So first let us see an application of this. So again, this is the partial character table of S4. So we have actually used the same trick in S3, but here we will see S4. So again you have the trivial character and then you have the sign character, just as a sign of these permutation in the conjugacy classes. Now this pi of S4 is a permutation character, so this just is talking about number of elements fixed. So it's fixing the number of elements. So let me write pi of S4 right here. So identity, it fixes all the elements. So S4 has 1 2 3 4. This is, it fixes all the elements. So 4 elements are fixed, 1 and 2 are permuted, so 3 and 4 are fixed, 2 elements are fixed, 1 2 3 are permuted, so only 4 is fixed, so 1 element is fixed, none of the elements are fixed, so 1 2 3 4, none of the elements are fixed. So this is our pi of S4, our permutation. So this is elements fixed by G, where G corresponds to the conjugacy class. So now we are saying this chi of U, which we from this pi of S4 minus this trivial, gives you an irreducible character. So 4 minus 1 gives you 3, 2 minus 1 gives you 1, 1 minus 1 gives you 0, 0 minus 1 gives you minus 1, 0 minus 1 gives you minus 1. So we get this entire irreducible character. This irreducible row we get just by doing this subtraction, and that is the purpose of this. So we have seen the application of this, and this is precisely because we have the S4 is two transitive on this. So now we have to prove this lemma. So first recall that you can write this pi of X is M1 1G M2 this character plus MK this XK trivial character. So this we have seen. Because our group G can decompose into vector spaces, and corresponding to those vector spaces, then you can take the characters of those vector spaces, these are the multiplicities, and that is what adds up here. So you have, this is the trivial character, and these are the multiplicities mi, so they are positive integers. So this we already know from the decomposition of our group G into whatever vector spaces we have, v1 n1 so on to vk mk, sorry, m1 v1 m1. So now you take the inner product of with itself, so you get mi square. Now so this also we have seen before. So now this, using this pi x1 x2, using this lemma, you know this is the number of orbits on x1 times x2. So now x1 x2 is x, so this is the number of orbits on x times x. So we are copying this thing right here. So setting the number of orbits as 2, so that is, in other words, G is 2 transitive. So either they are the same or they are different. So if you set the number of orbits as 2, this pi xx we are saying is number of orbits is 2. So you're setting this as 2. So if you set this as 2, you have to have this k as 2. So this is just m1 square plus m2 square, which has to be 1 square plus 1 square. So m1 is 1, so this is 1, this is also 1, this chi2 we are writing as chi, so that is done it. So this pi of x here, this pi of x is equal to this 1g, because m1 is 1 plus, instead of chi2 we are writing general chi, and that is what we wanted to prove, as you can see. And we have seen the application of this. So we have for S3 also the same trick. You know the trivial and you know the sign representation, and you just see what are the elements fixed by G, and then you subtract the trivial to get another row. So we have actually computed the entire character table of S4 in a previous lecture, but this adds more sense to that lecture.